Hello everyone, welcome to Lab 7. In this lab we'll be discussing volcanoes and hotspots. My name's Joe and I'll be the TA for this lab. If you have any questions throughout, please feel free to email me at schultz.61@osu.edu. Alternatively, I'll be hosting office hours on Wednesday from 3:25 to 5:15. Please see Carmen for the Zoom link if you wish to attend these office hours, and I strongly encourage you to do so if you have questions. All right, before we get into the nitty-gritty details of volcanoes, I just wanted to try to motivate this lab a little bit. Why do earth scientists care about volcanoes? Why do we study volcanoes? So here's just a couple examples. This list is by no means complete, but I think it does a good job of motivating the study of volcanoes or the field of volcanology. So when the Earth first formed, much of the water we see on the surface and then the gas that makes up the atmosphere was actually trapped in the mantle and was released to the surface through volcanoes because these are basically our natural vents, our only direct pathway to the mantle. So they're hugely important and basically allowing these volatiles to escape from Earth's interior to the surface, and obviously the Earth's atmosphere and surface water is imperative to the habitable nature of our planet. So, without volcanoes, the Earth would not be habitable, at least not to life as we know it. Furthermore, volcanic ash often contains minerals that are beneficial to plants. So in a large-scale eruption, you can have ash that travels very far from the volcano and that gets incorporated into the soil. And if you have many volcanic explosions or eruptions over a long period of time, basically you can cover much of the earth with at least some sort of volcanic ash that is then incorporated into the soil, which is and lets plants actually grow in the soil. And then in your rocks lab, you should have talked about some of the commercial applications of igneous rocks, which form from volcanoes. So as lava, which is just magma that's reached the surface, cools, it forms igneous rocks, and then also you can get igneous rocks forming in the interior through cooling, and all of these rocks have one commercial application or another. Furthermore, volcanic eruptions unfortunately can be very destructive and cause large loss of life and economic damage. So as earth scientists, it's important for us to understand volcanoes as well as we can so that we can predict when and where these catastrophic eruptions will occur and minimize the loss of the damage done. So the goals to this lab are first to understand how and why volcanoes form, which settings, the different settings that they form, and their strong link to plate tectonics, which you hopefully were exposed to a little bit during the plate tectonics lab. But volcanoes are closely related to, are coupled with plate tectonics. We'll also learn how calderas form, what exactly a caldera is, and the main controls that determine how much elevation is lost during an eruption, and then also why some volcanoes are more explosive than others. We'll look at two great examples of calderas, namely Mount St. Helens and Krakatoa. And then finally, we'll take a look at hotspot volcanism and how it's useful as a tool to determine plate motion as a function of time. So we can use hotspot volcano chains like the Hawaiian Islands, which we'll take a look at to figure out the rate and direction that a given plate is moving, even 80 to 100 millions of years ago, when obviously we didn't have GPS capabilities to allow us to determine plate motion at those times. So for this lab, you should start, if you haven't done so already, and complete the pre-lab reading. It's only a couple pages. It shouldn't take you more than 5 minutes to get through. Uh, and then, so watch the Caldera lecture clip, which I'll actually talk about here. Then complete the Caldera exercise. Uh, and then watch the second lecture clip, which is on hotspots and hotspot volcanism. Complete the hotspot activity, and then finally, if you're feeling motivated, complete the Olympus Mons activity. So Olympus Mons is actually the largest known volcano in the solar system, located on our planetary neighbor Mars. I think that this exercise does a good job of tying all the topics that we'll discuss in this lab together. So I strongly encourage you to attempt this exercise, and it is for extra credit. All right, so first we're going to talk about the tectonic settings of volcanic activity. So there's four main types. There's continental rift, continental volcanic arcs, hotspot volcanoes, and volcanic island arcs. And so I have a YouTube clip that I think does a great job of explaining these four different settings. It's not the most exciting, but it has good illustrations, and it's pretty short. Uh, but hopefully, as you watch this clip, you'll notice that basically, with the exception of hotspot volcanoes, all of these other volcanic settings are very near plate boundaries and are actually, the result of plate tectonics causing these volcanoes.
Hi everyone. We're going to look in this animation at how the movements of the Earth's plates controls volcanic activity on the Earth. Let's look first at what's called continental rift volcanism. Now, in places where forces are causing the Earth's plates to stretch, especially in the continents, a couple of different things can happen. In this part of the animation, you can see there's what's called a rift valley, where the crust is ripped apart and it sinks down to form a valley. That's kind of like the East African Rift Valley, or much of the western United States in Nevada is like this. Or you can simply get cracks in the crust that will allow magma from the mantle to rise up. In either of these situations, what we call continental rifting, we get volcanoes to form because as the plates separate, it allows the mantle to rise upward. Really what happens is the separation of the plates depressurizes the mantle underneath. There's not as much weight on top, and that reduction in pressure allows the hot rock of the mantle to actually melt. Now, more important even than that is the kind of volcanic activity that happens is associated with subduction. In this animation, we're going to subduct some ocean floor underneath the edge of a continent. And as that happens, as you know, you get an ocean trench, but at a certain depth, about 80 miles down in the Earth, the subduction of the plate triggers melting of the mantle, and that magma rises, and a whole series of volcanoes begins to pop up along the edge of the continent parallel to the trench. We call this a continental volcanic arc. The Andes Mountains are a classic example of such a system. Now, another thing we can do is have, instead of ocean floor subducting underneath the continent, we could have ocean floor subducting under other ocean floor. In this case, the animation is flipped around, but it doesn't really matter. You can imagine either of these in a mirror image. Same process. We're going to subduct the ocean floor underneath this other ocean floor. We're going to generate magma. The magma is going to rise, and a whole series of volcanic islands is going to pop up in the ocean parallel to the trench. You see how it's very similar to the continental situation. The only difference is that the volcanoes are popping up out of the ocean parallel to the trench instead of on land parallel to the trench. Okay, so an example of this would be the Aleutian Islands, say, or the Philippines, or the Marianas Islands in the Pacific. These are all what we call volcanic island arcs. Now, the other main source of volcanic activity on Earth are what we call hotspots. Hotspots, in a situation like this, there's magma being generated all along a long line. Hotspots are situations where magma forms in just one local area. And we think these hotspots form because of large blobs or columns of magma that rise from deep in the mantle. We call these mantle plumes. Mantle plumes. And as tectonic plates move across mantle plumes, if mantle plumes stay in one place, and there's controversy about whether they do, but let's assume the plume stays in one place, it'll make a volcano. The volcano will get carried away. Another volcano will form. It'll get carried away on the moving plate. And yet another volcano will form, and it'll get carried away. And you get a chain of hotspot volcanic islands. This is a classic example of how, for example, the Hawaiian Islands formed, all in a line, one after the other, as they moved across a hotspot. Let's back this up again, and we'll show one volcano, then another, and then another, forming over the hotspot. So those are the main reasons and processes by which the Earth makes volcanic activity.
Okay, so hopefully that clip gave you a good idea of the different volcanic settings and how they're related to plate tectonics. So, plate tectonics' role in volcanism, with the exception of hotspots, which are, you actually find in the interior regions of plates, far away from these plate boundaries. And so we'll touch on these on hotspot volcanoes later, and why we care about them, since they're not immediately linked to plate tectonics, but they do serve as an important tool for, like I said, determining plate motion as a function of time. But first, let's talk about calderas. So, in short, a caldera is the collapsed magma chamber of an eruptive volcano. So basically, a volcano is supported by a magma chamber, and when it goes through a catastrophic eruption, you're actually, some of this, depending on the size of the eruption, some of this magma chamber will be depleted, leaving basically just empty space, and will take away some of that pressure support that had been there prior to the eruption. So the overlying rock will actually collapse due to the force of gravity into this the vacated areas of this chamber, and so you'll lose some elevation in this volcano, and it'll form a crater-like structure, which is known as a caldera. The major controls on how much elevation is lost and how large a caldera will be are the size of the magma chamber and then also the scale of the eruption. So if you have a large magma chamber and a small eruption, you're not going to vacate very much of the magma chamber, and so a lot of that pressure support is still going to be there, and so you might see a small elevation change or even none at all. Whereas if you have a large scale eruption, say in a smaller chamber, and then you can empty out almost the entire chamber, and so then there will be a large, you'll take away most of the pressure support, and there'll be a large volume of space that needs to be filled, because it's providing no pressure support, and so you'll have a lot more room for the rock to collapse into, and so you'll see a huge elevation change in a large caldera, and we'll take a look at two examples, Mount St. Helens and Krakatoa. But this, caldera formation and the fact that we see a large distribution and like changes in elevation due to eruptions, and caldera sizes, begs the question, why are some volcanoes more explosive than others? I have another little short clip that I think does a great job of explaining and demonstrating why some volcanoes are more explosive than others.
Hawaii's volcano Kilauea has been intensely erupting for the past few days, spewing lava from new cracks in the earth and forcing some residents of the Big Island to evacuate their homes. But this volcano has actually been continuously erupting since 1983, and at least for an active volcano, it's usually pretty chill. We tend to think of volcanic eruptions as these fast, epic, explosive disasters like we see in the movies. So why are some volcanoes like Kilauea typically more gentle, and why did it suddenly get so destructive? Well, Kilauea is what's called a shield volcano. These guys look like broad, domed warrior shields, and they're formed when, after a period of years, layer after layer of runny lava pours from the volcano and hardens. Runny lava can more easily release trapped gases. It typically bubbles out of the earth more fluidly, so super high pressures don't tend to build up inside the volcano. That's why shield volcanoes rarely erupt explosively. The more explosive volcanoes tend to have more sticky or viscous lava that traps gas and pressure. So anyway, for years, Kilauea has been pouring lava from its main vent and also from fissures which are surrounding cracks in the earth. But recently, something changed inside the volcano that made it more difficult for the magma to flow along its usual route, and the pressure built. And as a side note, magma is just what you call lava when it's still underground. Anyway, scientists aren't exactly sure what happened inside the volcano, but the magma naturally looked for another way out, breaking rocks as it moved. And it happened to find a weak spot in the crust in a residential area on the slopes of the volcano. Scientists are getting better at measuring changes inside volcanoes and predicting when they might erupt, but there's still much more to learn. So volcanology is a field ripe for future scientists to make their mark, and in the process, save people's homes and their lives.